So we'd like to go ahead and get started to make sure there's any more of Laura's time. And we're really pleased Laura here with us. And this webinar is actually co-sponsored by the Yale Center for Methods in Implementation and Prevention Science, CMIPS, the Yale Center for Interdisciplinary Research on AIDS, CIRA, and particularly the Dissemination and Implementation Science Core, and the Implementation Science Coordination Initiative. In addition, it's brought to you by the READY Hub, the Rigorous, Rapid, and Relevant Evidence Adaptation and Implementation to Ending the HIV Epidemic Implementation Science Hub. And we provide technical assistance ending the HIV epidemic projects. And we also, in collaboration with the Implementation Science Coordination Initiative, ISKI, also work to create opportunities to really translate local knowledge into generalizable knowledge across projects and across jurisdictions around the United States. So I want to introduce Laura. And sorry, there we go. So Dr. Laura Forastiere is an assistant professor in the Department of Biostatistics at the Yale School of Public Health. Her methodological research is focused on methods for assessing causal inference for evidence-based research and exploring the mechanisms underlying the effect of an intervention, including causal pathways through intermediate variables or mechanisms of peer influence and spillover between connected units. Her research explores modeling, inferential, and other methodological issues that often arise in applied problems with complex clustered and network data, and a standard statistical theory and methods are no longer adequate to support the goals of the analysis. So we look forward to her sharing some of those methods and giving us a clearer sense of how they can really help us better understand causality and impacts of interventions. Go ahead, Laura.
Thank you, Debbie. Can you guys hear me? Yeah? All right. So thank you, Debbie. I'm really happy to be here presenting my work in this seminar series. So today I'm going to be talking about my work on the identification of influential and susceptible individuals in studies with spillover effects. So before I start, I guess I have to say that I'm not that used to this type of audience. I'm more used to statistical audience. So I'll try to make things as clear as possible. But if you have questions, clarifying questions, please let me know and I'll be happy to clarify things for you. If you have more complex questions, perhaps let's leave them to the end. All right, so, okay, now the problem. Okay. All right, it's going on. So this work deals with the phenomenon, the mechanism called interference, which means that a unit outcome is also affected by the treatment received by other units. And clearly this phenomenon, this mechanism is present in many settings. Think of vaccines that are beneficial for the whole population, even if part of it is not vaccinated. And this is because if I get vaccinated, then I'll be less likely to get infected. And so I will not infect others if I'm not infected. But also, even if I do get infected, the vaccines reduce the infectiousness. So I'll be less likely to transmit my infection to others. Interference is also present in education, social media, but also in behavior interventions. For example, think of interventions like training or incentives to reduce risky behaviors, or like quit smoking or protective sex, for example. So those who receive the training and do change their behaviors are likely to also influence others in doing the same. Now, the problem is that when there is interference, then this causes statistical challenges, and we will see later that potential outcomes in this case can no longer be indexed by the treatment only received by one unit, but they have to be indexed also by the treatment received by others. So again, interference is present if given to units, to friends, for example, 1 and 2, then the treatment of the first unit, for example, a bed net or a vaccine, not only affects its own outcome itself, but also it affects the outcome of the other unit. and vice versa. So we usually call this effect of a unit's treatment on its own outcome, we call it direct effect, whereas we call the effect on a unit's outcome of the treatment received by other unit, we call it spillover effects. Now, in recent years, many methods have been developed to estimate this kind of effect, the average effect on a unit's outcome of the treatment received by other units on average. However, this spillover effect could be also heterogeneous. In fact, the different people might be affected differently by the treatment received by others. They might be influenced differently by the treatment received by others. And also different people, if treated, might affect the outcome of others in a different way. So to clarify, let me focus on behavior interventions because I think heterogeneity is easier to understand here. So in behavior interventions, spillover effects are mainly due to the behavioral influence among peers, among friends. And there could be two types of heterogeneity in two different directions. So there could be an heterogeneity with respect to what I call the sender, which is essentially the extent to which each unit, if treated, will affect his peers, his friends' behaviors. And this could be due to the fact that each unit may respond differently to their own treatment. And so this could be due to the heterogeneity in the direct effect, because if they don't respond to their own treatment, they will no longer influence their friends, but also could be due to the heterogeneity in the influential power. Different people, if they have changed their behavior, might influence the behavior of others in different ways. And now there can also be an heterogeneity with respect to the receiver. So in the other direction, meaning this is the extent to which a unit outcome is affected by the treatment of their peers, because different people might be more or less susceptible to the influence of others. So in this work, we will define causal estimates and develop estimators to assess how these heterogeneities depend on the individual characteristics. And then we will leverage these heterogeneities to develop heterogeneous treatment allocation strategies that essentially assign the treatment with different probabilities to different people. So in the first part, we will talk about the first aim. And in the second part, if I have time, depending on how many questions we have, we will talk about these treatment allocation strategies. All right. So let's start with the first part, the conditional influence effects. So here we are in a situation where units are partitioned into clusters. For example, think of villages or schools. And we do measure networks within these clusters. So for example, think of friendship networks within schools or friendship networks in villages. And as it's common in this setting, we make the partial interference assumption, which essentially excludes, rules out interference between clusters, but allows for interference within each cluster. So potentially each unit in each cluster can interfere with each other. And so how are we going to use the networks here? So we're going to use the networks to define the set of friends, because we want to estimate the influence that each unit has on its own friends, on its neighbors, marginalizing the distribution of the treatment over the other units in the clusters. So we'll see what that means in a second. So let me first introduce some notation. Let K be the cluster indicator, let I be the unit indicator in each cluster. Then we said that we have these cluster networks. Don't worry about the graph terminology, but remember that we let this NIK denote the neighborhood of unit IK. Now this is the network neighborhood, meaning set of friends or set of contacts in infectious diseases. Each unit then has a vector of characteristics X that we call covariates. And then we denote by ZIK binary treatment, for example, a training. And under the potential outcome framework, we denote by YIKZ the potential outcome of unit IK under potentially the whole treatment vector Z. Now, when we have no interference, we essentially only allow the potential outcome to only depend on individual treatment, ZIK. Whereas here, we replace this assumption with a partial interference assumption. So this is how we usually formalize this partial interference assumption. So essentially what we're saying here is that the potential outcome for unit I in cluster K depends on the whole treatment vector Zik in the whole cluster K. Now, let me first review the causal estimates that we usually define in this type of setting under the partial interference, and then we will define new ones. So usually what we do is we would extract the individual treatment from the treatment vector in cluster K, this Zik for unit Ik, and this Zk minus I would be the treatment vector in the rest of the cluster. So with this definition of potential outcome, essentially we would be able to define direct effects by comparing these potential outcomes where we change the individual treatment from 0 to 1 and we fix the treatment vector in the rest of the cluster. Whereas the spillover effect is defined by fixing the individual treatment and changing the treatment vector in the rest of the cluster from this vector Z to this vector Z prime. Now, the problem here is that these type of potential outcomes where we fix the treatment vector in the rest of the cluster at a specific value are not estimable, not even on average, because each unit will be observed under a specific treatment vector, and there are no two units that are observed under the same treatment vector. So what we usually do to overcome this problem is we draw the treatment vector in the rest of the cluster from a distribution. And usually we would use a Bernoulli distribution that essentially mimics a randomized experiment with the probability alpha. So we denote by Y bar Ik, Zik alpha, the average potential outcome of unit I in cluster K when that unit is treated with treatment Zik, and the rest of the cluster is assigned to treatment with probability alpha. In this way, the direct effects are defined by comparing these type of potential outcome where we fix alpha and we change the individual treatment, and the spillover effects is defined by changing alpha, so it's changing the probability of assigning treatment to the rest of the cluster and fixing the individual treatment. Here, instead, what we want to do is investigate the spillover effect, the inference effect of a unit treatment on the outcome of its neighbors, and investigate the heterogeneity of this. So essentially, instead of extracting from the treatment vector in cluster K the individual treatment Zik, we extract the treatment of a different unit, Jk, who is a neighbor, a friend of unit I. So in this way, the difference between these two potential outcomes where we change the treatment of unit Jk from 0 to 1 and we fix the treatment vector in the rest of the cluster would be the influence effect of unit Jk on unit Ik. Now, the problem is, as before, that we cannot estimate these kind of potential outcomes because where we fix these treatment vectors. So what we're going to do is draw these treatment vectors from a distribution, a similar distribution to what we had before, a Bernoulli distribution with probability alpha. So here we denote by Y bar Ik, this time Zjk alpha, the average potential outcome of unit Ik if its friend Jk was treated with this treatment Zjk and the rest of the cluster, including unit Ik, was assigned to treatment with probability alpha. So now the influence effect of unit Jk on Ik is defined by this difference in these average potential outcomes, Y bar. Then we take the average of these average potential outcomes across all neighbors of unit Jk, and we denote this average by mu Jk, 1 alpha and 0 alpha when the unit Jk is not treated. And this difference will be essentially the influence effect, the average influence effect of unit Jk on his neighborhood. And we denote it by tau Jk alpha, where this alpha is the probability that we assign to the rest of the cluster. So to make things more clear, let's consider this network. This is a network in a cluster K, where If you're not familiar with networks, these circles are the individuals, and these edges between individuals represent the relationships between them, friendship, for example. So let's focus on this unit JK, and let me represent by this red circle the treatment. So say we treat this individual JK. Now say that our outcome is a binary outcome, and we represent by this blue border the outcome equal to 1. So now say that when this unit JK is treated, it will have outcome equal to 1. He will, for example, if he receive a training, he will start using condoms. And by doing that, he will also influence these friends to do the same. Whereas if this unit is not treated, then only these friends will use condoms. So essentially, the inference effect of unit JK on its neighborhood will be the comparison between the proportion of those who use condoms among his friends when unit JK is treated versus when the unit JK is not treated. Now, the problem is that the outcome, the use of condoms for neighbors of unit JK might also depend on their own treatment and the treatment of their friends, right? So then if there is some sort of dependency between the treatment of unit JK and the treatment of his friends or friends of friends, for example, whenever unit JK is treated, then a lot of his friends are also treated. Then when we compare this setting where the unit JK is treated when the setting where he's not, we're actually getting not only the influence effect of unit JK, but also the effect of their own treatment, of the treatment of his neighbors. So to be able to have this fair comparison and actually be able to define the influence effect of unit JK, we essentially fix the distribution of the treatment among his friends and among the rest of the cluster with this probability alpha. So essentially, we change the treatment for unit JK from 1 to 0, but we fix the distribution of the treatment in the rest of the cluster so that we can actually define the inference effect of unit JK. All right, so now we have defined the inference effect of a specific unit JK. Now what we're going to do is take the average of these inference effect for each unit JK in each cluster K, denote this by tau K alpha, and then take the expected value of it, an expected value over a sampling distribution, where essentially our sample is considered a random sample of clusters from a target population. And so this tau alpha is the average influence effect of a unit's treatment on the outcome of its neighbors. Now, what we want to do is investigate the heterogeneity of this. So to do that, we consider two subsets of covariates, XS, where S stands for sender, and XR, where R stands for receiver. So for example, females and males. Say we want to estimate the influential effect of females when treated on their male friends. So to define these type of influence effects, we will take an average of these individual average potential outcomes only among units of types, friends of type XR, for example, males, for all females, for all units JK of type XS. So we denote this average, this conditional average among neighbors by this mu JK, where we fix this XR, where this XR is the type of neighbors. And so this difference when the female JK is not treated or is treated would be the influence effect of female JK to neighbors of type XR, to male neighbors. So then we take the average of these conditional average potential outcomes among males, among all females in cluster K, then we take the expected value of it, take the difference when the female is not treated or treated. And we denote this by tau, XS, where XS is, for example, female, XR, where XR is, for example, male, and alpha. So this would be the average influence effect of females when treated on their male friends' outcome when the rest of the cluster is treated with probability alpha. So for example, here we would just focus on females and we would only take the proportion of outcomes among male neighbors. So how do we estimate these effects? So the problem here is that these type of potential outcomes are usually not observed. Because we would need to actually have these Bernoulli distributions, and that should be our randomized experiment, whereas we could also estimate these potential outcomes where we have an observational study or we have different types of randomized experiment with some dependency between the treatment. So what we're going to do is use an IPW estimator that essentially uses the observed outcomes among the neighbors and weights units depending on how their treatment vector is compatible with the counterfactual scenario that we want to estimate. So essentially what we're going to do is take the average observed outcome. This y-obs is the observed outcome of unit IK. Take the average of this among all neighbors of type X among all males, for example, for each female, and we denoted this by y bar obs, and we will use this as our outcome of an IPW estimator. So essentially, we will take for all females of type XS, so all females in a cluster K, we will take a weighted average of these y bar obs, essentially the average outcome among their male neighbors, only for females that are treated with this Z of interest, for example, 0, 1. And the weight will be this ratio, where in the numerator, we have this probability of the treatment vector in the rest of the cluster under our hypothetical distribution alpha. And we divide by the estimated cluster level propensity score. So in this way, we essentially weight more those who have a treatment vector in the rest of the cluster that it's more likely to be observed under our hypothetical distribution, hypothetical treatment allocation with probability alpha, and that it's less represented in our observed data. Then we take the average of these estimated conditional average potential outcomes in each cluster K, and we take the difference of these estimated average potential outcomes when the unit is treated and when the unit is not treated to estimate these inference effects, again, for example, from females to males. It turns out that under our partial interference assumption, unconfounded assumption, and positivity assumptions, this IPW estimator is unbiased. When we have, so earlier I defined this IPW estimator for the case where we have categorical covariates. When we have continuous covariates, we can clearly not take these sample averages. So instead here, we rely on a model, a marginal structural model for this mu JK, this average potential outcome. A model that depends on the characteristics of the sender JK and on the average characteristics of the neighbors as receivers and, for example, an interaction between them. So we fit this model using a weighted regression estimator, regressing the average observed outcomes among the neighbors, all neighbors, on the average covariates among all neighbors, and on the covariate of unit JK. And we use the same weights as before. Now I'll skip the inference part. So essentially the idea is that to estimate the variance, we can either use a block bootstrap where we resample clusters, or we can use an M estimator. That takes the form of a sandwich estimator. Let me skip this, but let me show you the simulation study. So here we simulate 500 data set with 500 clusters and 50 individuals per cluster. We draw a treatment from a two-stage design, where essentially in the first stage, each cluster is assigned to a probability 0.4 or 0.6. And then in the second stage, units are randomly assigned to treatment under that probability assigned in the first stage. Then we draw two covariates, for example, two binary covariates, X1 and X2, for example, gender and education. And we let the potential outcome depend on this covariate, so that there is an heterogeneity with respect to both the receiver and the sender. In particular, we simulate continuous outcome from a normal distribution with expectation equal to this linear model, where we have the individual treatment, the number of treated neighbors, an interaction between the number of treated neighbors and covariates of the receiver of unit IK, and then the number of treated neighbors with these covariates equal to 1. So for example, those that are females are highly educated. So in this case, with this model, this beta 3 represent the heterogeneity with respect to the receiver, whereas beta 4 represent the heterogeneity with respect to the center. In our simulation study, we varied these parameters, beta 3 and beta 4, to generate 3 scenarios: one where there's only heterogeneity with respect to the receiver, one where there's only heterogeneity with respect to the sender, and one where there's both type of heterogeneities. And then in each scenario, for each data set, we apply our IPW estimator. So this is what we get. So here we show the bias, empirical standard error, analytical standard error, and coverage for these 3 scenarios for these 4 types of influence effects. So the first one is essentially the average influence effect, where X coincide with the overall X. So that's why it's the average. So it's the average influence effect from any type of sender to any type of receiver of neighbors. This second one is the average influence effect from senders with covariates equal to 1 to all types of neighbors. Third one is the average influence effect from all types of senders to receivers only with covariates equal to 1. And the last one is the influence effect from specific type of senders with these covariates equal to 1 to the same type of neighbors. So here we see that the bias is close to 0 in all scenarios. The analytical standard error is close to empirical one, and coverage is close to the nominal level. But what it's interesting is to compare the standard error across these scenarios. So first of all, we see that this when we estimate these conditional effects, when we condition both the sender and the receiver, the standard error is clearly higher. And also it's higher for this last scenario when there is actually heterogeneity with respect to both sender and receiver. So this is the scenario where the standard error is higher. In these other scenario, when there's only one type of heterogeneity, the standard error is higher when we look for the heterogeneity that is not there. So for example, here, we look for heterogeneity in this second row here for this first column. We look for heterogeneity with respect to sender, but there's only heterogeneity with respect to receiver. So in this case, compared to the other type of heterogeneity that we look for, this variance will be higher. And same here, but inverted. All right, so now we applied our approach to this randomized experiment about new weather insurance for rice farmers in China. So essentially, farmers were randomized to receive an intensive information session about this new weather insurance. So this is our Z, our treatment, and we look at its effect on the weather insurance uptake. So this uptake is our outcome Y. We have 185 villages with a total of 5,300 households. And we also observe friendship networks within each village. So here, interference is likely because clearly those who do receive the intensive session might disseminate the information they receive to their friends. And also, if they do buy this weather insurance, they might also convince others to do the same. So here, what we estimate is the spillover effect, the influence effect of a farmer receiving this intensive information session on the average purchase of this weather insurance among his friends. And we will look for the heterogeneity with respect to these type of characteristics: education, gender of the head of the household, risk aversion, age, and whether they did experience a disaster in the past year. So this table represents the point estimates and the confidence interval of all the influence effects. Here, the influence effect from these type of individuals. So the row represents the senders, and the columns represent the type of neighbors, the receivers. So each.
Can I ask you a question? Can you say,
sure,
what does the number mean, 0.112, in terms of this application?
Yeah. So so this one is the average. So this, you're talking about this one on the up left corner, right?
Just as an example, because then we know what all the others mean too.
Right. So this, if you see, this means from all to all. So this is essentially the influence effect from any type of individuals who receive treatment to any type of neighbors. So this would be the influence effect that each farmer will have if they receive their training, the intensive information session, on the average, on the proportion of the probability of purchasing these weather insurance among his friends. So essentially, this, what we can see is that when a farmer did receive the intensive information session, they increased the probability of purchase among his friends by 11%.
Okay, so that's perfect. That last sentence, I think, says it all.
Yes, on average, right?
Yeah, on average.
On average, from any type of farmer to any type of friend, right? Mm-hmm. But then when we look at these other columns and rows, we would see, we can investigate who's more influential and who's more susceptible. So if we look at this first column, then this would be the influence effect from these type of farmers to all type of neighbors. So we can see, for example, if we compare males and females, we can see that, well, both of them seem to be influential on their neighbors, on their friends, but in the opposite direction. So males tend to convince their friends to actually buy this weather insurance, whereas females tend to do the opposite, tend to convince their friends not to buy this weather insurance. And it could be because the more information these female farmers had, the less they were convinced about it. Then we can also look at other differences, for example, between the highly educated with the low, those who are low educated, and we can see that highly educated farmers are more influential, though the difference is not significant. We can also look at those who experienced disaster in the previous year, compared to those who didn't, and those who didn't seem to be slightly more influential than those who did. Younger farmers seem to be a little more influential than older farmers, although again, the difference is not significant. And clearly those who are more risk averse will be more likely to convince their friends to buy these weather insurance. Now let's look at who's more susceptible. So to look at who is more susceptible from the influence of any type of farmer, we would have to look at the first row, here and here. So here we compare, if we compare male and females, males are slightly more susceptible, highly educated individuals are slightly more susceptible. Even those who experience a disaster are slightly more susceptible than those who didn't. And also, again, those who are risk averse are also definitely more susceptible than those who are not. And also, finally, if we can see who is more influential on whom, right? So, for example, if we look at this, these estimates here, we can see that those who did not experience any disaster in the prior year are more influential to those who did experience a disaster in the prior year. And this could be because those who didn't experience any disaster, so didn't experience any loss in the previous year, perhaps already had a weather insurance. All right, so quickly, how much time do I have?
You have 15 minutes, Laura.
Okay, sure. So quickly, let me talk about the second part on heterogeneous treatment allocation strategies. So the idea is to leverage these type of heterogeneities to develop a treatment allocation strategy that would assign treatment differently to different units. So the idea is that if we have limited resources, essentially we cannot treat everyone, then it would be good to select a subset of individuals that, if treated, would maximize the average outcome on the whole population. And clearly, this subset of individuals have to be individuals who would respond to the treatment themselves, so who have a high direct effect, and also who would influence the rest of the population more, so who would have a high influence effect. Now, the investigation of the heterogeneity that we've seen before would give us some insight into good candidates for this. The problem is that when we have outcome diffusion, for example, this happens with behavioral changes, where essentially if I receive my training, I change my behaviors, I influence my friends to do the same, and then my friends would also influence their friends to change their behaviors. If we have this cascade of behavioral change, then this influence effect clearly goes beyond neighbors. So those who are more influential on average on their friends are not necessarily good candidates for this subset of individuals, because we will have to look at their network position. So for example, if they only have, say, those who are more influential only have one friend on average, then clearly they would not spread the behavior that much, because they will only spread it to that one friend. Or we would have to consider the clustering of similar individuals. So usually similar individuals cluster together. So if more influential individuals are friends with each other, then clearly giving the treatment to them, to the more influential individuals, would prevent us from reaching those who are in the periphery of the network. And we also have to look into the neighborhood structure. So if, for example, those who are more influential have their friends that are less susceptible, they would clearly not be able to influence their friends. And so we would have to consider all these factors to be able to select these the optimal subset of individuals to treat when we have limited resources. So this is what we're going to do. We will investigate hypothetical conditional treatment allocation that would assign treatment to individuals with different probabilities depending on their characteristics. In particular, we consider these type of hypothetical treatment allocation depending on a set of covariate XC with this probability of treatment, whose logit is this linear model that depends on these characteristics XC. So this gamma represents how we make this probability depend on these characteristics xc. And the intercept here will be calculated such that the marginal probability of assigning the treatment is equal to desired alpha. Say we want to treat 50% of the individuals, so this is how we're going to calculate the intercept given gamma. So with this hypothetical treatment allocation, we define marginal individual average potential outcomes, y bar ik alpha gamma, where essentially we draw the treatment vector in the whole cluster from this hypothetical treatment allocation. So this pi HP is the distribution from the hypothetical treatment allocation. So essentially the probability of each treatment vector given the hypothetical treatment location, parameterized by gamma and alpha. And then we take the average of these individual average potential outcome in each cluster K. And we define our estimate of interest by taking the expected value of these average potential outcomes given two type of conditional strategies where essentially we give more or less probabilities to different people as parameterized by these gamma. So we compare two gammas, a gamma and gamma prime. Actually, in particular, later we will compare a non-zero gamma to a zero gamma. So a zero gamma is essentially means that we assign the treatment at random regardless of their individual characteristics, where a non-zero gamma means that we actually assign treatment depending on the individual characteristics. So we denote this by OE, which stands for overall effect, comparing to, again, a gamma and in this case, a zero, fixing the marginal proportion probability of treatment to alpha. The IPW estimator is really similar to what we had before. So here we take for each cluster, a weighted average of the observed outcomes, where weights are similar to what we had before. The numerator here is the probability under this hypothetical distribution. The denominator is the estimated cluster level propensity score, so that we essentially give more weights to those who have a treatment vector in their cluster more compatible to the hypothetical allocation that we want to estimate. As before, this IPW estimator is unbiased under our assumptions. We conduct a similar simulation study to what we had before, drawing treatment in the same way and the two binary covariates. Now here we draw the two binary covariates with some correlation between them. And the outcome is drawn in a different way. So here we essentially draw the outcome to have some sort of heterogeneous interference with respect to the proportion of treated units in the whole cluster with x1, with a covariate x1, for example, gender equal to 1. So the outcome depends on the individual outcome depends on the individual treatment, clearly on their own covariates, but also it depends, because of interference, it depends on this T is the proportion of treated units in the whole cluster, and this T prime x1 is the proportion of treated units in the cluster with x1 equal to 1. So in this way, this represents the heterogeneous interference, right? Because we can investigate this, whether there is a different effect, whether the outcome would change if we assign the treatment differently depending on the probability we assign it, depending on x, if there is this type of heterogeneous interference. So here in this simulation study, we varied this beta 3 and beta 4 so that we have essentially a setting where we have no interference when both beta 3 and beta 4 are 0. where we have a setting where there is only homogeneous interference, so this beta 4 that depends on the proportion of treated units with x1 equal to 1 is 0. And then we have two settings where there is a moderate and a strong heterogeneous interference. We also vary the correlation raw between x1 and x2. So remember here that the outcome depends on the proportion of treated units in the same cluster and on the proportion of treated units with x1 equal to 1. So here the heterogeneity is driven by x1, not x2. So here we see the estimates of the overall effects and their confidence interval, where when we vary the gammas on the x-axis, we have the gamma compared to a random allocation strategy where gamma is equal to 0. Here we have the no interference setting, homogeneous interference setting, moderate and strong heterogeneous interference. The first raw is for a hypothetical treatment allocation strategy where we target x1. So essentially, we consider assigning the treatment differently to individuals depending on their value of x1. So gamma is on x1, whereas the second and third row is for targeting on x2. So here we can see that if there's no interference, or if there's only homogeneous interference, so the interference only depends on the overall proportion of treated units, then it doesn't matter who we treat. So the overall effect comparing an heterogeneous treatment allocation strategy with a random one is 0. Whereas when there is heterogeneous interference, then the overall effect would be non-zero when we target x1. So in the first row here, because there is heterogeneous interference with respect to x1, we can see that if we give a higher probability represented by a positive gamma to those who have x1 equal to 1, then the overall effect will be positive. So we'll have a higher average outcome among people in each cluster, and negative if the gamma is negative. When in the second row where we consider a conditional treatment allocation strategy that depends on x2, because actually the underlying heterogeneity does not depend on x2, then if the two x1 and x2 are not correlated, then it doesn't matter if we give a different probability to individuals depending on their value of x2. So the overall effect here, where we change gamma on x2, will always be 0, both for moderate and strong heterogeneous interference. But here, when there is correlation between x1 and x2, then the treating with higher probability, which is represented by a positive gamma, those who have an x2 equal to 1 will give us a higher average outcome among units. So here, so when x2 is correlated with x1, so say in the case where x1 would be the variable driving the heterogeneity, but say it's not measured, then we can also, instead of targeting x1 that we don't measure, we can target x2. So we can assign the probability of treatment depending on x2, even if the heterogeneity actually doesn't depend on x2. How much time?
Hi, Laura, if you could.
Unfortunately, 3 minutes, Laura.
3 minutes.
Okay, then I'll skip the diffusion scenario. So this is another simulation study where we have networks. Earlier, we didn't have networks. And the reason why we have networks here is that typically we always say that it would always be, when there is this type of behavioral changes in a cascade, it would always be better to give the treatment to those who have more friends, so that they can spread the behaviors to more people. So here we have a scenario where that is actually the case. When we have this diffusion process and we show that giving the treatment to those who are more central, who have a higher number of friends, is actually better, will actually give us an overall effect. So I'm not going to show you this simulation study, but what I'm going to show you in this in the 2 minutes that I have left is the results of this second approach. I'll also skip this test. The result of this approach in our randomized experiment among farmers in China. So earlier we investigated who is more influential on whom. Now what we investigated was who should we treat, right? So for example, here we look at different characteristics to see if we gave the treatment with different probability depending on that characteristics, what does happen? What would be the overall effect compared to giving the treatment at random? So here, for example, we focus on a characteristic being the rice production area, so the area of rice production for each farmer. And here we see that we shouldn't give the treatment with higher probability to those who have a larger area, because perhaps those who have a large area of production will already have weather insurance, will already be protected. But we should actually give the treatment with a higher probability to those who have a lower area of production, because perhaps they would respond to the intensive information session themselves by purchasing the weather insurance that they wouldn't have otherwise, and perhaps they would also influence their friends in doing the same. I didn't say it, but we developed a statistical test to actually test whether the overall effect is flat or not. So essentially whether assigning the treatment depending on each characteristic does matter, whether the overall effect is non-zero. And in this case, we reject the null. So actually, it does matter whether we do give the treatment with a different probability depending on this type of characteristic. Then here we investigated a hypothetical allocation strategy that is focused on degree. So degree in network terminology is the number of friends that each individual has. And as I said earlier, the usual idea is that we should treat those who have more friends because they are more likely to spread the outcome, the behavior to more individuals. So here we investigated actually giving more or less, giving the treatment with more or less probability to those who have a higher degree. And we distinguish between villages with small villages with less than 80 units and large villages with more than 80 units. Because we saw that depending on the size of the village, the networks were different. So here in the small villages, we see that you see the estimate of this overall effect with depending on gamma on degree. So here we see that we should actually, as expected, give a higher probability of treatment to those who have a higher degree. And this will lead us to a higher overall outcome in the population. On the contrary, in larger villages, we should actually give a higher probability to those who have a lower degree. This might be counterintuitive, but the reason for this result is because when you actually look at the networks, in large villages, the networks are sparse. So essentially, there are a lot of people in the periphery that have few friends, and those who are in the center of the network, who have a lot of friends, who have a high degree, they're all clustered together. So they're all friends with each other. So if we give the treatment to those people, then we're not going to be able to reach the rest of the population. So actually, compared to giving the treatment with higher probability to those who have more friends and are in the center, it's actually better to give the treatment at random. Actually, it's even better to give the treatment to those who are in the periphery and have fewer friends. And then when we do this analysis, yes.
Laura, we do need to break in.
Yes,
we are over time. And this has just been, so you want to just say this summary at the end?
Yeah, sure. So we develop an IPW estimator. We first define causal estimates and develop an IPW estimator to investigate the heterogeneity of influence with respect to senders and with respect to receivers. We then develop an IPW estimator to investigate treatment allocation strategy, to essentially investigate who to treat. And then we also develop a statistical test to assess the presence of heterogeneous interference with respect to each characteristic. Thank you.
And thank you. This is, as you've highlighted, the implications of what you're doing is really important in targeting and in leveraging limited resources. There was one question in the chat that I will send you via email.
Okay.
And we really appreciate the work that you're doing, and you're taking the time to share this with us today.
Sure. Thank you. Thank you for listening.
Thank you very much.